So my warm greetings. Good morning, good afternoon, good evening, depending on where you're joining us from. After, I think, a short break, the Center of Excellence in Astrobiology is back with another innovation seminar. And we're doing this as part of the Institute Innovation Council's plan of events. And we have recently started a new project in collaboration with the Berkeley SETI Research Center at University of California, Berkeley, in collaboration with Dr. Vishal Gajar. And now, as part of that program, we have selected 4 junior research fellows who are on our campus here at Amrit University, Mumbai. And as they are undergoing their training, we have planned a series of webinars. And the first webinar is being given today by Dr. Howard Isaacson. Howard, it's a pleasure to have you with us today.
Thanks for having me.
And Howard is a research scientist at University of California, Berkeley, and he will be talking to us in giving us an insight into his ongoing work, and perhaps for the students who are listening in, also perhaps a few tips on how they go along. And this is actually an opportunity for all of you to ask questions. So if you have any questions, you can just type them down and keep them in the Q&A section or the chat section. We'll be monitoring both of them, but it'll be great if you can find the Q&A section and just list them there. And we'll try to take them towards the end of the talk. And if there's anything else you'd like to just kind of ask privately, you can also keep those questions aside. We'll also share the email address of some of us, so you can send us the questions in case you can't take them. So Howard, over to you, and looking forward to hearing your talk.
Thank you very much. I will first attempt to share my screen here, see if this works or not. All right, can you see my screen?
Yes, it's coming through fine.
All right, and I'll keep my video on, but if the bandwidth doesn't work, just let me know. I can turn that off, maybe that'll help. So thank you very much for having me. Today, I'm gonna be talking a little bit about our efforts at Breakthrough Listen to answer one of the most profound questions in astronomy, and that is, are we alone? And we are searching for signs of artificial intelligence, signs of technology beyond the Earth, signs of intelligence. We name them Technosignatures, one of the words you'll hear thrown around. And of course, more traditionally, we're known as a SETI project. And so all the work I'm doing today is sponsored by the Breakthrough Initiatives and Breakthrough Prize Foundation. And with that, I will jump into the talk. And so I've changed my title a little bit here. I've changed it to Searching for Technosignatures in Optical Astronomy Data rather than High Resolution Spectroscopy, because I've wanted to broaden the topic a little bit in terms of what we'll be talking about today. So I'll touch on a couple of our other projects that are ongoing. And so I'll be talking mostly about data that we collect with the Automated Planet Finder Telescope, which is high resolution optical data. We'll go into some detail about that. And then I'll touch on the TESS telescope. That's NASA's TESS satellites, the Transient Exoplanet Survey satellite, and some work that we're doing there looking for technosignatures. And I'll talk about some of the other projects we have ongoing with Breakthrough Listen. And so to begin with, I thought I'd tell everyone a little bit about how I became involved in Breakthrough Listen. So I've been a researcher here at UC Berkeley in the San Francisco Bay Area for about 12 years. And when I joined UC Berkeley, I was working for support on the Kepler Space Telescope. So the Kepler spacecraft was launched in 2009. Its purpose was to search about 100,000 stars in the northern sky in an effort to find Earth-sized planets that were transiting their host stars, right? Transiting meaning that they cross between us and the face of their host star, dimming the light a little bit. As we monitor the brightness of those stars, we see a little blip when the planet crosses right in front. And of course, Kepler was hugely successful in finding all kinds of facts about other solar systems that we didn't know about, including the commonality of planets between the size of Earth and the size of Neptune, sort of 1 to 4 Earth radii. Here's a picture of it here on the left before launch, and the launch itself on the right. Kepler was in an Earth trailing orbit, and it's now nearly on the other side of the sun. It's more than an AU away. And it's retired now. It did great work with Kepler Prime and the secondary mission called K2. And it was such a rich data set of hundreds of thousands of stars with baselines in photometry, right? Brightnesses of stars, photometry, of about 4 years, that people are still publishing papers about all the great data that came from Kepler. And so this was the first project I worked on as a professional after my student work. I was a graduate student in San Francisco here, where I am now, at San Francisco State University. My advisor was Deborah Fisher. And after I finished studying physics there and doing a thesis in astronomy, I moved to Berkeley, where I've been ever since. So that's kind of how I got here. And one of the most important things that Kepler found, I can't really give any kind of talk without talking about this, because it's just one of the most amazing things that I think we've learned in the last 10 years. And that is that if you measure all these hundreds of thousands of stars and you see how many transit, and you correct for the angle of orientation for those that don't transit, and you learn something about all the host stars, you learn something about the planets. And we learned that if you consider just the planets that are about the size of the Earth, about 1 to 2 times the size of the Earth, and those that are about the same distance away from their star, right? Sort of like the habitable zone, also called like the Goldilocks zone, where if there's water present on those planets, it's the right temperature to be liquid water, depending on a lot of things, including the atmosphere. But if you just start with that, then it turns out that about 1 in 5 stars like the sun host a planet like the Earth. And this is just completely amazing to me. Like, I mean, we didn't, before the Kepler launch, we didn't know how many, if there was just one, if we were the only one, if they were around every single star. And now we know that if you look in the night sky, you can see about 1 in 5 stars that has a planet. It's really a remarkable effort of engineering on behalf of NASA and astronomers across the United States and across the world with international collaboration. So very amazing results from Kepler. And that's really what got me into astronomy professionally, and sort of how I ended up, after working on Kepler, to work both on Kepler and with Break to Listen. And my main work that I was doing when I was working on that was I was taking ground-based observations, following up targets from Kepler identified as planet host stars. These are the Keck telescopes in Mauna Kea in Hawaii. They're at 14,000 feet, so over 4,000 meters above the Pacific Ocean, where you're above about 50% of the Earth's atmosphere. So you get rid of that annoying part of the Earth's atmosphere, which of course is not annoying when you need to breathe it, but it's annoying when you're trying to observe the stars beyond the Earth. It's a remarkable place above the sky, above the Pacific. You can oversee clouds and other islands and amazing sunsets and whatnot. And the science that comes from these telescopes is truly remarkable. And the main instrument that I use, the Keck high-res spectrometer, is very similar to the APF spectrometer that I'll be talking about. And that's why there was such a nice segue between the work I did in exoplanets and the work that I'll be talking about today for Break to Listen in the search for technosignatures. So this is kind of a fun picture. Of course, it's a beautiful picture of the summit of Mauna Kea. You can see on the left here, 4 telescopes, Subaru on the left, 2 twin Keck telescopes, and then a 4th telescope here. There's about 13 telescopes total on Mauna Kea. And what you see shooting from the telescope into the sky is an adaptive optics laser. And it's convenient that we have this photo of the adaptive optics laser, because in the SETI sense, what we're looking for in high resolution spectra is exactly something that would resemble this laser being shot into the sky. So we're looking for something that we really have the capability of producing, which is nice. And the same, of course, goes for radio SETI. And so it's a great connection, right? We have the Keck telescope emitting this laser into the night sky. We turn that on its head and said, okay, let's use those same instruments on the telescope and look for what we're putting out into space. So I'll give a quick overview here of Breakthrough Listen. So Breakthrough Listen is a 10-year science project that uses telescopes across the world. So the Northern Hemisphere, the Southern Hemisphere. In the upper left is the Green Bank telescope. It's 100 meters across. It's the largest steerable structure on land. You can point it at nearly any star in the sky in the Northern Hemisphere, and it's incredibly sensitive at detecting radio signals. So we wanted to have a complement to that telescope in the Southern Hemisphere, so we could have full sky coverage. And on the right-hand side, we have the dish, the Parkes 60-meter telescope, which is famous for receiving some of the very first transmissions that we had from the moon when astronauts first stepped on the moon. And so it's still used for science today, all these years later, despite including its historic past, it's still functional today. So those are our two primary radio telescopes coming online in this last few years, and in the future is the Meerkat telescope in South Africa, which is an array of telescopes, each 15 meters. There's going to be 64 dishes total, and it's going to be even more sensitive put together than the mighty Green Bank telescope once it's fully in action. And so that's something we're working really hard on bringing into the fold. The most recent telescope that we brought online with Break to Listen is the Veritas telescope on the bottom right. And these are Cherenkov telescopes used to measure particle showers from high energy particles as they crash through the atmosphere. They split into their component parts, and these telescopes are capable of picking them up and learning something about those components and where they came from in the night sky, things like that. So they now have a SETI component on them as well. And then finally, the automated planet finder at Lick Observatory. I'll talk more about that in the next couple of slides. Overall, the survey, the Break to Listen survey, both on APF and on the Green Bank and Parkes telescopes, is looking first at this primary sample of stars. And because we don't really know what the best places are to look for SETI signals, we've chosen some stars along the main sequence. We've sort of chosen some cool stars, which would fall in the lower right of this plot. Cool stars like Proxima Centauri, for example. The sun is sort of in the middle of this wiggle. This is the main sequence of stars here. And then as you move up and to the left, you get to the hotter stars, right? 6,000, 7,000, 8,000 degrees. All stars in the main sequence and then additionally some nearby giant stars. And all of these stars are within 50 parsecs, which is considered our solar neighborhood. And so we started with this. We have some other targets that we've since added, but this is the primary Break to Listen survey that we've been working on for the last 5 or so years. In the last couple of years, we have some TESS planet candidates. I'll talk about TESS a little bit later. And we've chosen some of the most nearby ones to observe with all the telescopes, Green Bank telescope, Parkes telescope, and the APF. In addition to these stars, we also sort of have some flexibility about what we like to observe. For example, Oumuamua, which was a comet that flew through the atmosphere, through the solar system. We observe that. We observe nearby host stars that have planets that are in really close proximity that were found by other detection methods, such as the radial velocity method, the transit method of exoplanet detection. So we have some flexibility, but this is our bread and butter here. So at Lick Observatory here, I have in the middle photograph a picture that was taken off the Mount Hamilton webcam just a few hours ago when I was finishing up the slides. And you can see it's a not gloomy night, but a cloud-filled night with a little bit of scattered rain. So the APF here pictured on a sunnier day last summer will likely be closed tonight, protecting itself from the elements. Unlike radio telescopes, optical telescopes have to close during bad weather, and if there's clouds, they can't see through them, just like we can't see through them with our eyes. Compared, of course, that's in contrast to radio telescopes, that you can still do some kinds of astronomy when there's cloud and rain and things like that. You can view these webcams. I put up the website here, so you can click on them on your own and check out what's going on at Lick Observatory. And it's a place that we like to. It's only an hour from where I am now, here in the San Francisco Bay Area. And so we often take our summer students up to Lick Observatory because it's just a wonderful historic place to do science and to visit. So here's a picture from a few years back by Lori Hatch. There's a bit of snow on the ground. So again, not observing that night when we got all this snow. And here's the first image that you'll see of a high resolution optical spectrum. And I'm going to show several of these. And so to start us off, I'll just say that this covers sort of the standard optical range. So in the blue, you cut off at about 3,500 angstroms or 350 nanometers, and you can go up to about, in this case, 7,000 angstroms. Some optical telescopes go a little bit further into the red. And then once you get even further beyond sort of 9,000 angstroms, 900 nanometers, it's required to have different kinds of detectors. And so this is a sweet spot where you can get all of these wavelengths on a single detector. And of course, the laser lines we're going to be talking about are going to fall in just a very, very narrow part of this spectrum. And that's really the key to detecting them and determining if they're signs of intelligence. So on one of our tours, we got to visit both the APF telescope on the right here. Brad Holden, the project scientist for the APF, is showing the primary mirror. It's a 2.4 meter primary. And we're lucky enough to get them to sort of point the telescope down on our tour, and we could take little selfie pictures and pictures of each other on the primary mirror, which is super cool. It was a beautiful day that time in the summer. You can see some of the students taking selfies, and in the bottom left, you can see the dome of the great refractor, a 36-inch, so nearly 1 meter refracting telescope built in 1889, and used for, it's still the largest optical, it's still the largest telescope in the world that uses a lens, a 36-inch refracting lens. Of course, there's bigger telescopes that use mirrors, but this is the biggest refractor, and it's quite a special place to visit. So a special place to visit and still doing great science. And so here is sort of a generic high resolution spectrum. We'll look at some actual data in a moment. I've mentioned the wavelength coverage you have here, and now we can start to dig in a little bit and see what sorts of things are possible. So I like to think of this as sort of the matrix where, you look at it once, it looks kind of confusing, and there's some dark spots and some colored spots. And then after a little bit of time, if you look at it enough, you can start to see the patterns that represent, for in this case, different elements. In the matrix, they talk about buildings and cars and things, but in this case, we can start to see these features that really are prominent. And so at the very top, you can see these circles are encompassing the sodium D lines. It's a doublet. So there are two absorption features that are prominent in solar type stars. You might notice this color, this orange color where the sodium D lines are, is similar to streetlights at night. So low pressure sodium and even sodium LEDs or sodium colored LEDs are that color because they're in this wavelength range. In the middle, there's the magnesium B lines. These are pretty prominent lines used to measure the gravity of the star. So the gravity of the star tells you something about how much pressure there is on the star, and whether it's on the main sequence or whether it's inflated, making it a subgiant or a giant star. And so these lines in particular are good for measuring that property of the star. And in the bottom here, it's sort of melding together with the background, but nonetheless, if you were to focus in on those and study them for several years and measure a bunch of different stars flux in these regions, this is the calcium H and K lines, you might write a thesis about it. So my graduate thesis at SF State was about these very tiny bits of spectrum and this whole wide range of what's available. And so if you look really closely, the type is really small, but my whole senior thesis is in that little tiny area right there. Graduate thesis. Okay, enough of that nonsense. So we have a resolution of about 100,000 in the middle of the optical range, which is about 50 nanometers. You can see the actual coverage here that we have on the automated planet finder. It's one of the really cool things about it is you don't need to stay up all night anymore to do the observing with the automated planet finder. It is in fact automated. So we submit our targets at the beginning of the night. They're combined with other groups' targets prioritized. And when the sun goes down, the telescope opens and begins to observe them one by one when things go well in a completely autonomous fashion. So it's a pretty amazing piece of technology. So we've been looking at this overall spectrum in the upper left, which I've talked about in the last slide. And if you were to just take one of those slices out, we call that one order or one segment of the spectrum, and you were to zoom in on it, you could get this plot on the left, and you can see some prominent features, including those magnesium B lines in the middle column, middle row. The H alpha line, bottom right, very prominent, one of the very first spectral lines discovered. Sodium D lines, which I mentioned, and then some iron lines, the calcium line up above. Again, one of these, it's basically the type of thing where you look at it long enough and it all starts to fall into place and make sense. So back to optical lasers. So here's another picture of the summit of Mauna Kea. This is a nighttime picture, but the full moon is up, and so some of the light is really reflecting off those telescopes, making them really quite bright. You can see here the Milky Way. The Gemini telescope is off picture to the left. The two Keck telescopes are in the middle, Subaru telescope on the right, and they're all at the same time looking at the galactic center, making measurements of the supermassive black hole at the galactic center. And so this is a pretty phenomenal photograph. And again, these laser lines that they're shooting out, again, in this case, they're that same sodium orange because they're sodium lasers powered by sodium, and not powered by, but emitting at those wavelengths that sodium emits at. And yeah, that's what we're gonna look for. So how do we do that? How do we look for these these laser lines. Let's talk a little bit about this. So those previous graphics that I showed were nicely colored, rainbows. And of course, when we collect a spectrum of a star with the APF, we don't have those colors, but we know that the positions of these lines, in the top and the bottom, left and right, have assigned wavelengths. Of course, that's what the spectrum does, right? We spread the light out of each individual star into its component wavelengths, and we examine them in kind. And so here we have a spectrum of a sun-like star. These features up here, if you can see my mouse on this part up here above the 60 line, these are lines that are from the atmosphere, so-called telluric lines. And it's the oxygen in the Earth's atmosphere and the water in the Earth's atmosphere up in these lines that absorbs that light from the star and creates these absorption features. And they're in every single spectrum despite the temperature of the star, because we looked at the atmosphere in order to observe all of these stars. And you can see these other lines that are down lower, and you can see that they are somewhat sharp. And so some stars have quite sharp features, but other stars have more blurred out features. And you can either have a really hot star that does this, or a star that is really rapidly rotating. So here I've replaced that spectrum before with a rapidly rotating star. And I'm highlighting both the telluric features up at the top with that orange-yellow arrow, and these white dots, which they don't look like, look like all sort of vertical dashes. And these are essentially our nemesis when it comes to detecting laser lines. So these are cosmic rays. So these are high energy particles that pass through interstellar space. They come through the Earth's atmosphere. They even pass through the coverage of the detector, so they don't bounce off the optics of the telescope and the spectrometer. They actually pass directly into the CCD, and they make a little scatter. They excite some electrons in there, and they come up to when we see them as cosmic ray hits, and they're really problematic, and I'll tell you why here in a second. And so again, we have these really broad features from the star because it's rapidly rotating. We have some sharp absorption features from the night sky, which are always present. And then we have these little blips all over the place, which are cosmic rays. Again, let's talk about more about those. So if you were to look at just one horizontal slice of this spectrum here, the APS spectrum, you would see these cosmic rays pop up above the average flux. So this arc across the order, so from left to right, is an artificial part of the spectrometer, how it works. So you can imagine that this is sort of represents an average amount of flux across this part of the spectrum. But more importantly, you can see these three spikes that represent the cosmic ray hits, and they fall sharply above the average. And again, that's the sort of thing that we're looking for when we look for laser emission lines. We're looking for things that are in addition to the star's light, and so fall above what we call the continuum level of the star's emission. We're able to see them, not the cosmic rays, but the potential laser lines, because we compress them. We compress that energy incredibly tightly into a very, very narrow wavelength range. And only by doing that can you start to outshine the star, or have an emission feature that's as bright as the star. You can see it above that background star's flux. Okay, so here's a more detailed look at the types of things that we're looking for. So you can see, let's start here on the left. You can see in this image up above here that the stellar order is this sort of bright left to right crossing event. And there's one little blip here about 33 pixels in. And it's obvious because it falls below the primary stellar flux. And if we were to compress that, right, just do a vertical sum of every pixel in this order, we would see the average flux along almost all of the pixels. But then we see this one spike, again, represented by these pixels here, and that's a cosmic ray. It's important to note that almost all the flux from the cosmic ray falls into just this one pixel. Okay, so maybe it falls into 2 or 3 pixels, and as you can see here, each circle represents the center of the pixel. And those two are above the continuum, but more importantly, just this one pixel is above. And so when we run our laser detection algorithm, we know that because it's just that one pixel, all the flux is compressed, that it's a cosmic ray. And the reason we know that is because when the starlight from any star that we observe with the APF passes from the primary mirror and the secondary mirror, and then the directional mirror, the tertiary mirror, into the spectrograph, and all of the optics inside of that, the shell, grating, the cross disperser, prisms, then it it gets what's called an instrumental profile. So an imprint of all of those collective bounces and reflections through every element of glass and off of every element of glass, such that the narrowest thing you can measure is the narrowness of what's called the instrumental profile. And in this case, on the right-hand side here, we can see that it's not just this 1 pixel, but it's now sort of 1, 2, 3, 4, 5, 6, sort of 7 pixels, right? So if you take just the top, it's 3, 4, 5 pixels. Now this is getting more interesting, right? Now we're getting to the point where, okay, it's not a cosmic ray. You can see that it's more than 1 pixel. We can see on this right-hand image, right, the stellar light is this left to right bar, and we see that this interesting signal is both brighter than the star at this very narrow wavelength range, and also extends a little bit beyond where the star's light, vertically beyond where the star's light falls. And this is not a laser candidate, but a night sky emission line. And even though, so that light did have to pass through all the optics of the telescope, so it matches the point spread function. But we see that because it's vertically taller than the star's light, we know that that's coming from the night sky sort of quote unquote surrounding that light from the star coming down the spectral slit, spectral opening of the instrument. So it's a little bit technical, talking about what's called the point spread function or the instrumental profile, but it's really the main way that we figure out if laser candidate lines are cosmic rays, night sky emission lines, stellar, related to the star, or perhaps something else. So this is a couple of papers that have been published in the past. So sort of a literature review, if you will, about the search for laser emission lines. These were both, the one paper on the left, the David Lippman paper, I'll tell you about the author in a moment, but this was done on automated planet finder data of Voyager star, which is a really interesting SETI target because it's provided a very unusual light curve from the Kepler Space Telescope. So a lot of stars are sort of typically flat. They're typically cyclical and periodic, and this star, Voyager star, was very erratic in its light curve, and so it caused a lot of stir in the SETI community and in the astrophysics community because it was just really fascinating and was studied a lot. And so we wanted to. It was proposed that this unusual light curve was from some sort of artificial source, some sort of intelligent source, and so we followed it up and tried to see if we could see direct signs of that in the spectrum. On the right here, this is a pretty fascinating graphic because you can see that, again, a single stellar order from the star going left to right. You can see around 2 angstroms here, this sort of bright red streak, that's a cosmic ray. But more obvious in this graphic are these green vertical bars. And what happened is we were on the summit of Mauna Kea, and I was observing the telescope this night, this was years ago, and we had a collision with it was a light collision, so to speak, with one of the lasers that was being used on the summit. So the adaptive optics lasers produce an artificial star and the sodium layer of the atmosphere. And normally it's really hard to hit it on purpose because it's very, very tiny in the sky. And so we actually pointed our telescope right at it. And the star that we were looking for was in the background. So we observed both the background star and the laser itself. And this was the result of that. And so in the laser search, it comes up as a candidate. And it's dismissed because you can see again it's taller than the star's profile, and so we're looking for something that sort of matches the star's profile. But nonetheless, a really fun bit of observing that we did a few years back. Okay, well, that's sort of the main bit about adaptive optics lasers and about high resolution spectroscopy. We have some ongoing work, which I'll mention is being conducted by some of our junior members of our group. But that's not the only way you can do optical SETI. So that's how you can do optical high resolution spectra SETI. But there's also ways to do it that involve things like the Kepler Space Telescope, I mentioned Voyager star, and also the new Transient Exoplanet Survey Satellite, one of NASA's missions. It's flying right now. It's in orbit. It's collecting data as we speak. It's going to be a nearly all sky survey, looking again for planets that cross directly in front of their host star, causing a little dip in the amount of light that's seen. Each time the planet goes around the star, you see that same little blip. And if it's periodic enough, if it's periodic and it's significant enough, you can learn about the planet that way. And again, follow it up with spectroscopy and then try to do statistics on it and look for technosignatures with it. So this is pretty cool, right? So now we have this new ability to measure a huge amount of the sky, but in a totally different way than we're doing one star at a time with the high resolution spectroscopy. So it's a little bit different strategy though. I wanted to say something about how, well, I've said something about how we detect the potential laser lines and optical spectra because we're looking for something that's really, really compressed in wavelength. You can do the same thing by looking for signals that are really, really compressed in time. We do our radio search, we're looking for things that are really, really narrow in their profile. And all of these things are outside of what's expected in what I would just call sort of standard astronomy or astrophysical processes, right? Because all of the astrophysical processes that we know about tend to provide signals that we can observe on the Earth that are quite broad. They're broad in time, they're broad in wavelength, they're broad in frequency. And so looking for things like looking for anomalies with the TESS spacecraft allows us a different kind of opportunity because we're now looking for changes in the star's brightness over time that have to do with something that's beyond, potentially around the star if it is artificial. Okay, more about that in a moment. So here are some of the publications that we've put together. The first is by David Littman, which is remarkable because he was a junior and senior in high school here in the US in the Bay Area. At the time that he was doing this work, he came and visited our lab one time on an open house day. He's like, this is pretty cool. I want to do a science project. And one thing led to another. And pretty soon we put together a little paper that looked again for laser lines from Voyage's star. So it was pretty fun to have him involved in that at that level. And then one of the things that we do here at Break the Listen is that if someone makes a claim about a SETI detection, which happens more than you think, we typically re-observe that star with our instruments that include Great Meg Telescope, Parkes Telescope, APF. And we did that for a claim that someone would say, no, we found these, we did some Fourier transforms on these spectra, and we found these signals that I'm sure they're aliens. So we had to say, okay, well, we're going to look too, we're going to analyze our own data. And we couldn't reproduce that once we did a similar analysis. And so we had to say, hey, not this time, back to the drawing board for you. So that was a fun project to be a part of. And then now we have a couple of students who are working on the next iteration of the laser search with APF data, Anna Zuckerman and Zoe Ko, who are both former summer interns, similar to the interns that are part of this call today through Break the Listen. And now Anna's working full-time with us after she graduated Brown University last spring. So we do have a great program, as some of you know, that's our summer internship program. And we make a priority within our group in general to have lots of students both in the summer and in the proper semesters, because we really think of it as training the next generation of SETI scientists, of scientists in general. Of course, it's a very, very relevant skill set that you have going through all these types of projects. People go on to work in the tech industry, they go on to be professors, they go into graduate schools, all kinds of things that you can do. But so we're really proud of the work that we do to get young people into science. Okay, a brief aside here. So I just thought it was worth mentioning a bit about sort of the way you can approach a problem, even if it's something that's not very well explored like SETI. If it seems like it's just this, where do you start when it comes to framing a scientific question, even if you think maybe this idea is sort of out there, which some people do, not me. The first one is to identify the variables. So for us, we use the Drake equation. I didn't get a chance to go into that today, but the Drake equation puts together all of these factors on the right-hand side here and tries to give an estimate of how many alien civilizations there are in the galaxy, for example. And this was put together years and years ago, decades, in fact, and just sort of as a starting point of like, okay, if we are going to do this, where do we start? And it was amazing because basically started from nothing, and you can do this for any kind of project that you're working in. So the relevant variables are star formation rate, fraction of stars with planets, the fraction of planets per star that might host life, how many actually host life. You can see where this is going. You get more and more detailed each time. You basically can say, take the product of all of these variables and you have some kind of fraction of how many stars have intelligent life. So again, where do you start? Okay, we got the variables down. What's next? Well, let's just start with things that we know. So we have a pretty good idea of the star formation rate. We have, we know how many new stars are formed per year on average in the Milky Way. So that's a good place to start. We know only recently the number of fraction of stars with planets that's called eta Earth, and so that was something that's been discovered in sort of the last 10 or 15 years, even 10 or 12 years since Kepler. And but that's sort of all we know in this big list of things. And so the next step is to just pick one of these and just dig down as deep as you can into it and try to figure out what the answer is. And so trying to find out what the fraction of planets per star with conditions suitable for life is something that's ongoing. People want to look for biomarkers, signs in the atmospheres of planets that they're hospitable. And you just kind of have to just go one piece of the puzzle at a time. And then finally, it's really important to, at every step of the way, to publish what you have, even if it's upper limits. And so some of the study work that preceded Breakthrough Listen didn't get published because they sort of said, oh, well, we didn't find anything, so maybe it's not worth it. But it's really important because even some of the most important science experiments in the last 100 years have started out by saying sort of very, very broad limits on, for example, neutrinos and how many neutrinos are out there, or the number of planets that are found around stars. And again, we're going to keep working from the study perspective to say, okay, we can put limits on how common emitting antennas are on the average star that's sort of 10 light years away. And by doing that, and by building on all of those steps along the way, you can get closer and closer to the answer of something that's really definitive. But you have to start somewhere. Okay, I've already said a little bit about TESS. It was fired on a Falcon 9 rocket a few years back. It's been just doing wonderful science, exoplanet science, astrophysics, lots of different varieties. And again, just wanted to emphasize the fact that this is different than that narrow time, narrow wavelength, narrow frequency aspect of SETI, and is more about anomaly detection. And there's some really smart folks down at NASA Ames and affiliated with Breakthrough Listen who are going through millions and tens of millions of light curves, trying to find the strangest ones using machine learning techniques and artificial intelligence, and trying to find that light curve that just doesn't fit among all the rest of them, because maybe there's something out there. It's an all-sky survey. It's going to observe about 80% of the sky. It's really a remarkable tool for astronomers. And this depiction here, there's some depictions of a variety of technosignatures and their sources here, but the prominent one in the foreground here is a Dyson sphere. And so it's artist conception, of course, and the idea is you can sort of wrap around a star a shape, a contraption, a construction, such that you're encompassing all of the star's energy, right? You can imagine just like using all of that energy for your own civilization. And to do that, you require this enormous structure, and that structure is going to affect the brightness of the star when you look at it from afar. And that's the very, very quick version of what people who examine TESS light curves for technosignatures are looking for. And then finally, I'll just touch on this new idea that's, it's an old idea that's being rediscovered and re-emphasized, and that is using the SETI ellipsoid for anomaly detection. And so the idea is that if you have some drastic event, such as the 1987 A supernova, which was in the nearby galaxy around the Milky Way, the Large Magellanic Cloud, the idea is that as that light moves outward across the galaxy, it's sort of like a beacon, right? If everyone who sees that now has some sort of 0 point on their clock to figure out if other people out there see that at the same time, other civilizations. And so with the Gaia Space Telescope data, and new surveys coming online, well, an old survey, for example, like the Zwicky Transient Factory, but new surveys like the Rubin Observatory, it's formerly called the Large Synoptic Sky Telescope, LSST. These types of new study projects are becoming more available to scientists, and so there's lots of exciting stuff sort of on the forefront. It's the front burner. It's just like just about to happen in SETI land. And as we bring more people into our fold of SETI scientists, then more of these really fun ideas get to be examined. So yeah. Finally, there's one other project I just want to mention that's called Panaseti, and that's led by Shelley Wright, who's a professor at UC San Diego. She's got a Fresnel lens in front of her here, and the idea is that they have a few of these Fresnel lenses that are in front of detectors that can measure nanosecond timescale events. Remember, I talked about compressing those events into time or frequency or wavelength. In this case, they're looking for ultra short pulses using these Fresnel lenses, and they've come up with this concept called Panaseti that you can build these low-cost Fresnel lenses with sort of off-the-shelf equipment as detectors, and basically look at the entire sky, or huge chunks of the sky all the time. And so that the goal is to increase the amount of the number of measurements we're taking by increasing the amount of area on the sky that we're collecting data from. And so that's a really fun project that's ongoing right now. And I'll leave you with my astronomers' daydreams, and that is that when astronomers like Michelle and I have a cup of coffee or sit around at the end of the day and chat, we think about things like detecting biosignatures and exoplanets, right? Some measurement that you can take, that you can figure out if there's even the possibility of life on some other planet. And that's number one. And number two is that, within our own solar system, I have depicted here the moon Enceladus around Saturn. There's these plumes that project water that's below these ice shelves in Enceladus, and maybe that's a great place to have life. Maybe there's life even within the solar system. That would be amazing to find that, right? We're the only place there's life. Even if in the solar system we found that, would just be an amazing discovery. And finally, the detection of some kind of radiation that's from intelligent life beyond Earth. And I've had to use our own technology against us here, right? This is the depiction of what the Voyager spacecraft signal, right, launched in the 1970s. When we look out into space and we see Voyager, this is what we see. It's this very, very narrow beacon with two little narrow beacons on the sides. It's definitive. We've tested our algorithms to make sure we can find this, because this is the kind of thing that we're looking for. Something like our own technology that's sort of now beyond our reach. And so, of course, for Sean and I, this is the one that we hope will be the next great discovery in astronomy, and this is what we daydream about at the end of the day. So with that, I'm all finished, and we're happy to take a couple questions.
Thanks a lot, Howard. That was great. It was indeed nice to see that, a bit envious actually, to see all of those scenic places where these observatories are built. But it was a nice kind of a tutorial to understand how exactly the data is captured and analyzed. So let's just, any comments from you, Vishal? Should we jump into questions?
Oh, no, thank you so much, Howard. I mean, this was great. I think this was really important that all of us, especially working in radio, get to know what's happening in the optical domain as well. So yeah, I also enjoyed it myself, although I've heard Howard's talk many times, but it is always interesting because he had some of this new stuff that he talked about today. I guess I have not heard about it. So it was certainly very interesting. Yeah.
Right. So let's jump into some questions. There's a couple of questions I can see here. And meanwhile, for the others who joined in probably a little later after I made my initial announcement, feel free to type out your questions in the Q&A, and feel free to ask, even if it's a very basic or question that's not technical. It's absolutely fine. The whole idea of these talks is to introduce you all to this field of research, right? So we are more than happy to take questions that are even of a very primitive nature. That's absolutely fine. So here's a question from Biswajit. He says, congratulations for the breakthrough candidate 1 discovery. At the later stage, came to know that it was due to the Earth's surface system, which caused due to the interference. My question is, what are the challenges for us to face such kind of problems, since in Earth, there are a lot of radio transceiver, which uses radio waves as long and short communication. What if the ETs are sending signals which has the same frequency that we are using on Earth? What parameter to be taken to differentiate between that?
Yes, good question. I'll take a crack at it. Maybe Vishal can answer as well. He's a bit more of an expert on that. But essentially, it's a very difficult problem. It's in fact the hardest problem about radio SETI is that there are many signals from everything that's wireless in our entire world, going to and from space, going from towers to cell phones, Bluetooth, you name it, it's in our data. And so the main way that we can find to distinguish something from afar from something nearby is that things that are not moving relative to the telescope, so things that are stationary around the Earth, that includes essentially every transmitter on Earth, provides signals that just fall straight down in our data. And that makes them really easy to tell apart from things that are coming from outer space. So anything that would come from space would be at a diagonal in our data, and that's due to the change in it's the drift rate. Maybe I'll let Vishal describe it, but essentially we look for these different shapes of things, and they're very distinct. And despite because there are so many signals that are indeed from Earth, we use really sort of advanced techniques like machine learning and things like that to try to help out. But yeah, maybe Vishal can add something to that.
I mean, I guess, Howard, you already kind of covered it, but maybe I can add a few things there. So especially for BLC1, that was definitely an interesting sort of signal. But as Howard pointed out, the intriguing part was that typically most of the signals that we expect to see from Earth-based signals typically don't show drifting. They all appear to be, as Howard said, at the same frequency. They don't show changes in frequency. BLC1 was interesting because it showed changes in frequency, and this can happen for a signal that is truly from ETI, because the Earth motion around the sun, as well as the Earth's rotation on its axis, causes the Doppler delay. So then there is a sort of relative velocity. Either your Earth is moving towards it or you're moving away from it, depending upon whether you're looking towards the east or west. You will see that there is, because of the Doppler effect, the signal, if it's transmitted at one frequency, you will not receive at that same frequency, but you will see the changes in the frequency as the sort of Earth rotates, as you said, as the velocity changes. So that is what was intriguing about VLC1, that it showed a drift, which was kind of what we expected from an ETI signal. Moreover, that signal didn't appear to be there when we looked at different part of the sky. It only appeared when we looked at this one particular target, which is the Proxima Centauri. But eventually, what we found was that the frequency that the signal was detected is something of an integer multiple of what we call RFI, or radio frequency interference. So there are lots of radio frequency interference that we have already seen towards different parts of the sky. We had not seen the similar radio frequency interference towards this part of the sky, but the frequency was more or less matching. It's to some integer multiple of these RFI lines. So it was some kind of a what we call intermodulation that might have been introduced, which caused us this false positive. But this is a challenge. The way we distinguish is in a best way possible. Is to basically look in a different direction. If you look at one direction and you see a signal, you look other way, and if the signal kind of goes away, that is an indication that signal was actually coming from that part of the sky. And in 99.9% of the cases, we can easily distinguish it. We can simply reject it. There are very few examples like PLC1 that persist. That's why it was very interesting, and we were able to kind of write a paper in Nature about it, because it was something of an effort in order to discriminate what exactly it is.
Thank you. Thank you, Howard and Vishal, for answering that. The second question is from Adhish Mishra. He asks, will the James Webb telescope play a role in favor of SETI, like in helping finding other planets? I'm guessing planets that could probably have some technosignatures.
Yeah, I can take this. That's a good question. So one of the primary things that people will use the James Webb telescope for in exoplanet science is to probe the atmosphere of a planet, to look for biosignatures like oxygen and water and methane. And some people who want to do SETI science are doing something similar. They want to use James Webb to look for artificial species in the atmosphere. So for example, chlorofluorocarbons, right, which are CFCs, these should be used in refrigerants on Earth. They're not naturally occurring. And so if we were to find something like that in an atmosphere, that would be strong evidence, maybe not conclusive, but strong evidence for some kind of machines that are creating this, or some aliens out there that are producing this for potentially some similar reasons. And so there are ways to use James Webb for study, but it's not necessarily the primary reasons.
Awesome. And I believe the launch is happening next month, right? So everyone's looking forward to that as well. Fingers crossed. For the longest time, yes. Okay. So there's no more questions in the question answer. I'm just looking at the chat. I see that there's a couple of questions there. Oh, hang on. There's a hand raised. Avinash, go for it.
Hi, Dr. Howard. Very nice talk. I just have a very basic question.
Sorry, Avinash, I think if there is some other audio echo, so if there are other speakers, maybe you need to mute either one or two.
Yeah, now I guess we fixed that.
Yeah.
So, like in radio, we are looking for these profiles, pulsar profile, which will be not matching astrophysical signal or RFI. So, in optical, how are we looking for spectral signature for active CT, that is for live like a intelligent signal? How are we looking for those signals which are like other than the blobs and the cosmic ray that will hit? How are we looking in those big data, because it's huge? So are we looking for each spectral light curves, or we are using some algorithm to filter some parameters out?
Yeah, good question. And so essentially when you take all of your, let's call them threshold crossing events, those are events that fall above some line that you've chosen to be above what you will consider an important signal to consider. If you do this for 500 spectra, 500 stars, you get hundreds of thousands of signals that are above this threshold. And so there are a number of ways that you can go through them. One of them is you check the narrowness of their profile. They need to be sufficiently wide. And then you check their vertical profile. So if you go to so you check their instrument profile. You can also check for their wavelength. So for example, say you have a bunch of signals that all fall in exactly the same wavelength, rest wavelength, observatory wavelength, in a bunch of spectra. You can conclude that those come from something that's in the sky, like a night sky emission line. For example, the most prominent one that we see in our data is from recombination of 2 oxygens and 1 oxygen to form O3 to form ozone. You get a photon out when that happens, and that photon is really strong, so there's constantly ozone being created. That creates this really strong emission line. So you can map those out because you have very similar signals in all of the spectra. And then hopefully the way your algorithm works is you get some that are just really hard to figure out if you can't really tell if they're night sky emission lines or if they're cosmic rays. And in those cases, you can observe them with a different telescope. You can reobserve them with the same telescope and look for repeatability, which will be one of the most important things to really confirm a signal of artificial nature.
Thank you, sir. That answers my question.
Thanks, Howard. So, all right, let's just go through some of the questions in the chat box. So there's a question from Biswajit. He asks, why optical over radio astronomy? What are some of the advantages?
Yeah, fortunately, it's not either or. We have the resources to do both. And so while we have more people in our research group that do radio astronomy because it's typically more favorable in terms of the specific things we're looking for in SETI. We have optical to complement that. And so one of our goals is to even further expand that wavelength coverage. We want to do near infrared SETI. We want to do X-ray SETI. We want to do any kind of SETI that we can, if someone can think of a way to create an artificial signal, we want to create a test, an experiment that can see if that's out there.
So thank you. All right, let me just go through these questions and then I'll get to Raghav. So Manojendu asks, what are the algorithms used in the searching for spectral and timing signatures?
Spectral and timing signatures. Essentially, everything that we use is custom. So we write the code. other astronomers have written parts of the code to help get it to a sort of a modern stage. But because SETI is such a young field, nearly all the things that we use to search for the particularly technosignatures are something that's been written by someone in our group. So it's all custom. Does that sound right, Vishal?
Mm-hmm. Yeah, absolutely.
Yeah.
There's no pip install find ET.
Yeah. Okay, so another question from Viswajit. What if we find an ET signal in any spectrum? Since the waves travel at the speed of light, it may take light years to send back a reply to them. Until then, Earth might have already been evaporated due to flames of the sun. So, yeah, what are your thoughts on that?
Yeah, I think a lot of SETI questions sort of wrap over into philosophy and these types of things. Of course, if it's too far into the distant future, I try not to worry about it because I can't control much of that. But the idea that you find something and it's real communication and you're able to reply back is an ongoing debate in the community. Some people say you should never reply. Some people say, yeah, of course, why miss the opportunity? I believe there's a series of books written by the Chinese science fiction writer. I can't think of the name of them, but they sort of play this idea out. So there's definitely some science fiction writers out there who've considered it, and that's kind of a fun question to think about in the science fiction realm.
So a question from Subramaniam Sadasivan. Can light curves be modulated deliberately to encode messages?
Oh, yeah, that's good. That's an interesting question. Yes, I mean, the way that people are thinking about how to do this include a number of possibilities. One of them is, right, you have to sort of allow for the fact that they have some kind of ability to build like really large structures. So if you said that they have that, you could imagine, like a series of panels that are going to orbit their star, and there was some pattern between the spacing, like Fibonacci's number or sequence or something like that. People have thought about the idea of sort of somehow creating a way to hide a transit. So you can imagine that a planet transits every 5 days and we see that signal. Well, what if they could create some structure where the sixth one is sort of hidden, right? So the planet doesn't transit or doesn't look like it transits. That would be something that we're looking for that we think is interesting, that might show some evidence of artificial intelligence. So yeah, I think there's lots of different ways that you could do it. As we get more and more sensitive, I think there's even more possibilities out there for detecting that kind of thing. Good questions.
Thank you. And Manajendu asks, is there any SETI initiative in the X-ray regime?
Ooh, not that I know of. Research opportunity.
Yeah. Okay. Right. So let's go to some of our JRFs. So Raghav, you can go next.
Hi. Thanks for a great talk. I have a question. So in your talk, you mentioned that the optical part of SETI follows up on some of the candidates that the radio part of SETI might suggest, and it also suggests some of the candidates for the radio part of SETI to look at. So while suggesting any new candidates, suppose, so what is the exact process then? How do you formulate that you want to look at a particular part of the sky to find new candidates, or is there like a particular strategy there that after you convey to the radio part of SETI and they follow up on it?
Yeah, good. That's a fun question. That's right up my alley in terms of like how we decide about where to point the telescope for things. For us, it's typically gone from planets, interesting exoplanets or interesting phenomena that were discovered that we chose to then follow up with radio. I think it's less common to find something interesting in the radio and then go observe it with the optical. And so some of the things that we have followed up include very nearby transiting planets. These are typically around M dwarfs. M dwarfs are nice, cool stars. And the thing that's nice about that is that when they have a planet transit, it can be in the habitable zone and in a much shorter orbit. And so those are much more easy to detect. And so Ross 408 might not be the right number. There's a number of other nearby stars that with planets detected in them, and we followed those up. People are really interested in, I didn't mention this in the talk yet, people are really interested in observing stars with radio telescopes that are in the Earth transit zones. This is not quite related to your question, but it's something that we think about. And the Earth transit zone is if we were outside looking into our solar system, if we were at the right angle in space, the right position in space to see the Earth transit the sun, well, they know that we're there, right? If they were to observe our solar system, they can tell that the Earth is there and it's in the habitable zone. Maybe they measured the atmosphere. And so maybe they're focusing their efforts to contact us, because they know that we're here. And so there's extra attention paid to stars that reside in this Earth habitable, or whatever. I lost the name of it, but the Earth transit zone. That's it. Did that kind of answer your question?
Yep. Thank you.
Okay, good.
Thanks, Raghav. Akshay?
Yes, sir. Hi. Thanks for the interesting talk, sir. So, just a second. Yes, sir. So I just had this question that, like, while in the radio SETI observations, we usually one of the reasons we look at the galactic center is because we kind of believe there's a large possibility of coming up with detecting a signal from there. One of the reasons being that the large stellar density there. So from any of your optical observations, have you ever come up with any sort of proof that there is indeed an exotic population of exoplanets in our inner galactic circle, or like any kind of any kind of proof that kind of collaborates with the idea of doing a survey of galactic center in looking for SETI signals in the radio band?
Yeah, so good question. Unfortunately, we don't know much about planets aside from statistics beyond sort of our immediate solar neighborhood. So because we are really good at observing bright stars, we know a lot about the stars that are nearest us. And for those that have done a radio velocity search, that's about 100 parsecs, maybe 200. And for the Kepler field, a lot of the stars were at a kiloparsec, so a kiloparsec, so 3,000 light years. Right. And remember that the galactic center is sort of 25,000 light years from the Earth. And so in that regard, we don't know anything about the potential planets that are there. And so we rely on the statistics that many stars, most stars have planets. And we sort of hold that truth to be, not everywhere, but, it's reasonable to think that there's planets around those stars.
Thank you.
Thanks, Akshay. Arun.
Hello, sir. Thank you for the interesting talk. I have a question. This is regarding how advantageous is an ET search when compared to, in the optical frequencies when compared to the radio frequencies, because we have this all the effects, all the atmospheric effects, and all those coming into play. Then I think radio waves are more easier to reach to the ground-based telescopes and all. And but how advantageous is then an optical-based observation for ET search?
Can you repeat just the very last sentence again? I didn't catch the very last sentence.
No, I'm asking how advantageous is an ET search in optical domain as compared to the radio frequency domain.
Yeah, it kind of goes back to the previous question about how we know about exoplanets, and that is that you're right. You can't see as far in the optical. Interstellar space would absorb a lot more quickly, especially in the optical for laser lines. So I think generally the parameter space is smaller, but nonetheless, if you think about like the sort of technology that we have that we're capable of producing, we are sensitive to that kind of technology, or maybe something slightly beyond that, as long as the stars are within sort of 1,000 light years. So I think beyond that, yeah, it starts to become really the domain of radio. Mm-hmm. Yeah, good observation.
Thank you.
We'll do what we can, I guess, is the rest of it.
Right. There's one more question in the chat, and I guess that's a question I'm guessing you guys get a lot, because we also get it in the ground-based astrobiology studies. Why haven't we made contact yet?
I think Vishal is sleeping too much. Likes to sleep all night instead of work all night. Yeah, no, I think it's a fun question to think about, and I think what we like to say in the lab is that we don't know if we'll detect a signal sort of on our watch in the next sort of few years or few decades, but we're pretty sure that if anyone finds one, it's going to be us, because we have the best facilities and we have a great brain power and collaboration. I mean, we could give a whole talk about just the collaboration that we have across the world. Of course, a lot of you being part of that collaboration. And so, we're doing everything we can. We're expanding the wavelength domain that we're interested in. We're expanding the sky coverage that we can handle. And, in this attempt to find the answer to really, one of the most interesting questions that you can pose, right? Are we alone? We're trying.
Yeah, absolutely. And that's something that's binding across so many different disciplines of science, and is kind of keeping things together. The whole idea of looking together for something is something that you wouldn't have even spoken or met a scientist, but as soon as you know that they're working towards answering that question, there's already a connection, whether that's a really senior scientist or a colleague or a student even who's studying. So I think that's a very beautiful thing. I see Akshay and Raghav, you have your hands up again. You want to ask questions, or is this from before?
No, so this is from the previous one itself.
Okay. All right. So you guys can
So
raise your hands.
I have a question. Sorry.
Okay. Yeah, go for it.
So my question is now more and more radio telescopes and interferometers are joining the radio part of SETI as a collaboration. So in the future, or even currently, are there any other optical telescopes you are partnering with for this initiative?
Yeah, good question. Let's see. So we have the automated planet finder, and we have primary time on that telescope. For these types of telescopes, there's typically a 1 to 2 year proprietary period. After that, you can download the data from online archives and analyze it. And so we can do that as well. We have done that. The Keck telescope and the high-res spectrometer has had its spectra analyzed. And the next procedure will be to, and these are both what they call slit-fed spectrographs. And so they have a spectral opening that opens into the optics of the spectrometer, and you collect the data. But the new way to do it, like the next generation of spectrometers, is to place an optical fiber at the focal point to then capture the light in the optical fiber, and then you can do all sorts of things with it that you can't do without that. The most precise radio velocity instruments are using these. They produce a different sort of profile on the CCD camera, and that'll be the next step. So that'll be the next collaboration. And the Keck telescope has a new instrument coming online next year called the Keck Planet Finder. It's been in development for about 10 years and is about to come on the telescope. There's the Habitable Planet Finder in Texas. There's the NUID telescope and spectrograph in Arizona. There's the HARPS and HARPS North spectrographs that are part of European Union work. And so there's all kinds of opportunity to collaborate, an opportunity to search more and more data that's really quite similar to the APF.
Thank you.
Thanks, Howard, for that. Right. So I see we have, I think, answered all the questions that I can see here. So, and we're also, I think, about a few minutes over time. So with this, Howard, that was an excellent session, I feel. It went really well. Thank you so much for taking time out and at short notice agreeing to do this. And our team is just kind of starting off. So we will need all the support and guidance, in the next coming months and probably even years to help build SETI research in India. And Vishal is, of course, our mentor and guru, who's kind of helping put all of this together from Berkeley. So thank you once again for this, and look forward to staying in touch.
My pleasure. Look forward to working more with you in the future.
Thanks, Howard. Thanks
Yeah,
a lot, Vishal.
Thank you all. Thank you for joining. Bye-bye.